Okay. All right. Okay, we have a couple things to do today.
No thanks.
Okay. All right. We have a couple things to do and to cover so that way you're ready for the actual homework you're going to get tomorrow. Today, there's a couple things we're going to do to make sure that you are paying attention, that you know how to solve things. You will definitely need a calculator so you can actually type some stuff in. So that way we know that we're all on the same page, that we know how to solve for a certain answer, all that good stuff. So here's the idea. First thing I'd like you to write down. We're going to write down the two formulas that we have. Okay, I'm going to try to separate these on the board. Here's the first one. Now obviously it's written differently if we look at other things, but this is the way that I'm writing it. The book will have its own terminology for it. The next one we have is very similar. I'm going to use the similar letters. Okay, these are my two formulas. One is exponential using the natural number. One is just exponential growth. So like, they mean the same thing. There's still similarities. I can show you how you can go from one to the other. They would give you the exact same numbers. It's just that one is using the natural number. This one is continuously growing at a constant rate. This one is just considered to be constant. There's a difference between continuous and constant. Because continuous will end at some point, or it won't reach a peak.
Didn't you use a K yesterday, or is it the same?
Yeah, it's the exact same thing. So I'm putting RK. It's the same thing. Like the letters don't really matter. It's just the concept of what they wrote.
So
okay?
wait, you said that E is continuous,
E is continuous.
and that reaches a peak.
No. E would just continuously grow at that same thing, as opposed to being constant.
So human population will never peak until it has to.
Until it has to, until there's like some other factor.
George, you want this?
So yes, just true. So okay, now here's the reason why I bring this up, because one of the questions that we're going to eventually get in the homework tomorrow is if they were to give you this formula, do you know if it's growing or shrinking? That's one of the things. That's what I want to show you right now. It's showing you two different examples. So this is going to be growth, constant growth for this first formula. So I'll just give you some random numbers in. So A equals 5, 1.05 to the 6. Or you can put, instead of 6, you can put a T there for all I care. I don't really care what they have. Here's how I know that it's growth instead. The number for R, this number right here, is above the number 1. That's how it's growing. It's growing actually on this particular problem, it's growing by 5% per time period. Okay, does that make sense? If it's in decay, so it's actually shrinking. So if it's in decay, then the idea is it would be something like this. That one's in decay by 5%. So this R is less than 1, but it's greater than 0. That's how you know it's decay. It's dropping by 5%. Constantly. Okay, do we understand the difference there? Just some people need to see that. Like you can see now, this is obviously the initial population or initial amount of a substance if you're doing something with like some type of element, some type of chemical. And then this would be the actual growth rate. And then this would be the time factor. It could be in minutes, hours, days, years. They'll give you that number. We'll do an example of that here in a minute. Okay, the next one. This second one here, over here. If I want to talk about growth, I believe we introduced this yesterday, but it was one of those things like we went kind of quick, so I want to make sure that you understand it. It looks like the same situation. A equals, let's go 5e, and then we'll put like 0.02t. I'll put something like that. That problem is growth. Now, the reason being on this problem is because this number right here, I believe we called it the K value, or the rate value, whatever you want to call it, K or R, that number is positive. It's above 0. That's how I know it's growing. It's different than this one. This one's saying 5%. That one's actually saying it's growing by like 2% or in that ballpark. I can show you what that actual number is here in a second if you actually want to know. Okay, questions at all about what that growth is? Now, that isn't the actual perfect percent. That's just the constant rate that it's growing. Okay, so if you want to know the actual percent, to change this problem back to one like this over here, all you do on your calculator is type e to the 0.02. You type this in your calculator, and it will tell you a number like 1 point something. And that's the actual rate that it's growing by, the percentage. So you'd actually have to figure out what e to the 0.02 is. That's how I can change it from one form to another form. That's the easiest way I can show you that. I don't think the book ever even discusses that you go from one form to another.
No.
All right. Questions at all about growth? Now, decay. Sorry about that. We talked about this yesterday. I just want to make sure that we covered it. Decay, same exact idea. There's a decay problem. What's the difference?
Negative.
Negative sign means it's going down. That's all it's telling me. So, better put it more down here. So the idea for decay is that this number is the k value or r value, whatever you want to call it, is less than 0. That's how I know it's going down. That's the difference between these two formulas. That's how I can look at it and immediately know am I going up or down. If it's concave up, if it's concave down, because maybe it's dropping off, that type of thing. All right. Questions at all about the concepts here? All right, now we have talked in the past, and I think even Sammy brought up, how do you know if a formula is going to have a limit or it's going to peak at some point? Typically what they'll do is they'll give you a formula like this, but what they'll do is it's going to be a very similar formula, but it will have something like this. Like this is telling me something. Like when they write a formula like this, it's got a limit. The limit is actually what would make this 0. Like you can't put in certain numbers. It's actually going to peak. The peak is probably this top number. That's probably what it's going to max out at. So maybe this is maybe millions or billions in population. Maybe the population of a certain type of animal can only reach 5.06 billion. So then the idea is that that would be your peak and you're dividing by whatever it's growing by. So then on a graph, this one, it'll look like it's climbing because it's going up by a certain percent, but then it's going to reach a peak at some point and level off because it will reach that 5.06 number. That's typically what the book will use. We actually had something very similar to that when we did pre-calc, if you remember back. We did ones where we did, I think we did something with like a flu and an outbreak of a bacteria infection or something like that. So where it would grow at a certain rate and it would peak when it either hits max population, total infection, that type of thing. But typically, like in censuses, they look at what the maximum population of the planet could be. I think our maximum population of Earth, I think they always say it's like 9 billion, but I'm pretty sure they're being conservative.
Aren't we already at 9
So,
billion?
no, we're
Close to
7.
8.
But I think they say it's supposed to be 9, but I think in theory, there's some number that says we can hit 12.
You said we're gonna hit the
So
maximum
you
capacity
know-
by the time you're 75.
Like,
think it's
yeah,
like
like
12
20,
billion.
what, 20,
It's like 20,
yeah, something like that. There was some number we calculated last year that we'll actually see it in like
Yeah,
real
you're
life.
only
So,
alive.
are you on board with that?
What?
Like, do you think that when we hit 12 million in like 2056,
12 billion.
I don't wanna live on over that.
or yeah, I meant 12 billion. Do you think that when we hit that number, that we're just done for?
No, I think there'll be, you'll see a lot more severe swings in populations. Like diseases will get a lot worse.
So you don't think that I will inevitably die?
From something like that?
Do you think it's possible?
I think
for
you
me
will
to
eventually
live-
die, I guess.
Well, you think it's possible for me to live to a crisp age of say 85 degrees?
Yes.
Or years?
85 degrees. I can, you have every right to live to that.
But if the world goes to crap in 2052, I'm only about 51 years old.
I'm not saying, I'm just saying that that's in theory what they're looking at. I think they're being conservative.
I think we got a tough time ahead, that's what I think. I think we're dead.
All right. Anyways, let's get to more of a more uplifting situation. All right. So here's the idea. Let me do an example here. This is something that I want to try to figure out. So let's say we're talking about a half-life of an element. Okay, half-life. So that means is whatever object you have, it'll be cut in half at some point. Okay? So let's say I don't even know the actual amount of substance that I have, but I know that there'll be half, and I want to know at some point during that process if it took the half-life and it took a time of 2,000 years to go into half-life. So if it went, so it took 2,000 years to go to half-life, something like that. And I can put any number in there. I'll explain these numbers here in a second. I want to know how much material would be left in 1950 years if I started with an amount of, let's say, 50 milligrams. It won't be completely halved, right? It won't be at 25 because I didn't reach the 2,000 years. But I'll be really close probably, right?
Yeah.
Because it took 2,000 years for this element to reach half. So, and that was in milligrams, let's say. I'll explain the numbers on that. I want to know what would be left out of 50 milligrams. So about 25, maybe 26, maybe 27, something like that. Okay, so now let's explain the formula here. The actual element itself, it went down by half. So it went from 1 to half. So this is the amount of milligrams I have. And now it went to half at some point. That's the easiest way I can say. That's the easiest way I can compute this. Now the problem is, we actually need to at some point be able to type this in a calculator so we can actually get the numbers that are involved here. And that's that's why I said I want you to have a calculator to understand how to do like exponential and all that good stuff. So, all right. So the first step, you always want to get the item that has the variable in its power by itself. So I'm going to divide by 1. So what's half divided by 1?
Half.
Now, if you had to, like if that was a weird number, like in a minute we're going to do 50. If you ever had like 50 over here and a 20 over here, you divide the 50 over. Just divide it over and write down that decimal. So half divided by 1 is still half. So here's what I'm left with. 2000K or 2000 R. I don't care what variable you pick. Now, to solve this, do you agree that this has an E, a natural number?
Yeah.
There's a variable up in its power. To get it to drop out of the power, you have to do a natural log. A natural log will, we have properties, it's called a power property. You're allowed to drop that power out front if you take a natural log of both sides. So I'm going to take a natural log of this side. I'm going to take a natural log of this side. A natural log is just an operation in math. It's kind of like squaring both sides or adding 2 to both sides. It's just an operation. We're comparing powers. And so when I take the natural log of both sides, what happens here is that when you take a log or a natural log of either side, the powers can always drop out front. That works for a natural log or a normal log. I'm picking natural log because I have an E in this problem. So I'm using it. So the 2000K will be out front. So I have a 2000K natural log E, those are being multiplied together, equals the natural log of half. Make sense? Like how I did that. Now, what happens to the natural log of E? Yeah, this literally cancels out. The reason being is what the natural log of E actually stands for. It means the log of base E of E. That's what it actually stands for. So I'm actually taking a log, I'm just picking the base that I want. And what power do you put on an E that makes E? 1. That's why this literally drops out. It is turning into 1. And you're multiplying it on 2000K. So the 1 will just go away. That's what it's doing. And now what you're allowed to do next is divide by the 2000. So this will help me solve what my K value is. So it's natural log of half, and when you type that in, you actually have to use a parenthesis there. Natural log, type in parenthesis 1 divided by 2, close the parenthesis off, then divide all that mess by 2000. Now when you do this, your K value probably should be negative.
Yep.
Because what's happening to my element?
Well, barely it's negative.
It's just like negative 0.0 something.
Oh, barely.
So So why did it turn out to be negative though?
Why?
Yeah, why did it turn out to be negative for this number? Why did I know it was
It's because
negative?
it's gonna be a subtraction.
What are we doing?
Decay.
We're halving, it's decaying. It's breaking down. So if it's decaying, yeah, the decay number better be negative. Duh, it's not growing, we're shrinking in size. Now, what was the number we're actually getting, like in terms of decimal?
Negative 0.00034657.
Something like that, is that right?
Yeah.
Am I way off?
Oh, you're pretty close.
6.5?
46574.
You don't worry about it.
Okay, there we go.
4.
All right, 4. All right, now, why I'm gonna use that? So I'm going down by less than 1% in theory. I'm going down by not even a fraction of a percent, it's going down really slow because it's taking 2,000 years for this thing to break down, so its percent's really slow. And now what I'm gonna do is go over to that problem and figure out what would happen in 1950 years, what would happen to 50 milligrams of something. Well, this is what I wanna know. How much is left if I had 50 milligrams, right, with a decay rate of negative 0.000346574, and I'm going 1950 years. I can just immediately start using that new number now because I know what my decay rate is. That's the K rate, the R number. I can plug that in. Now the problem that most people will have when they're typing this in for the first time, they will forget the parentheses that are involved on the E. Like on my calculator, if I hit the little E button, I don't even know where it's at on this one. There it is. If I just hit second and hit the little natural log, the E button, so the shift E, I don't even have to hit the little caret. It is automatically waiting for me to put in a power. Some calculators you have to be careful. So what I would do when I first pick up my calculator is figure out how do you type an E into your calculator, a natural number, and how does the power thing work. So if you want to practice this, what I would always do is try like putting a 2 in its power, because the natural number E is 2.7, so if I put power 2, it should be between 4 and 9. It's not quite, it's not quite 4 because it's not 2, and it's not quite 9 because it's not 3 squared, so it's in between. So for me, like on my calculator up here, my E button, I hit second, hit the little natural key, then I can type in 2 and hit enter. It automatically knows it's 7, right? 7.3. So if you're not getting that, you need to make sure you know how to type this in, because some calculators are all different how you type in E and how you type in powers. Sometimes they don't give you the little caret. You don't need it, you just type in the number behind it. But the problem is, what I have to make sure of is I have to make sure that both of these numbers are in the power, in that parenthesis. They have to be in the same parenthesis with the E. Because that's the number one thing people will get wrong. So E to the negative 0.000346574 times 1950, and then I'm going to close that parenthesis off. And so this number back here ended up being 0.508739 blah blah blah, and then I'm going to take that number times 50, because that's what this number turned out to be. That was the E to that crazy number. I'm going to take that times 50 milligrams. It ends up being 25.4. 43697. If I went really exact on my terms of numbers. So, was it nearly half-life? Yeah, it nearly got to 25. It was just a little bit above that. Because duh, it took 2,000 years for something to break down in half. We nearly hit 2,000 years. In terms of years, we're really close. Some people are like, oh, you're 50 years off. Yeah, out of 2,000. So I was expecting to be around 25. Okay, questions at all about how to use E and how to type stuff in?
Instead of breaking down the E separately, can't you just type it all in?
You can type it all in, hit enter. Yeah, I just want to make sure, the goal today was to figure out, can you type it in correctly? Can we get those right numbers? Because the most common mistake people make is this part right here. Because they'll type E, they'll type that, then they'll look at times 1950, and the calculator doesn't know what you just typed, so it thinks you're doing this. And it thinks you're doing this, where you're taking this small number times 50, then times 1950. So you have to be careful on where you put that 1950 at. Okay, questions at all?
So what? I lost my messing back up.
Are we done now? We're done?
What do I type in?
So we don't.
We're done. We're done.
Okay, are we good so far? So far, okay.
That was the last one.
Now, one more. One last round. I swear we'll be done.
You swear?
Swear.
Swearing's not
Swear like
good.
Oh,
that.
nice to swear, swear.
Should be saying
Cursing
naughty
is
words.
good. I swear.
50.
Cussing.
So swearing is okay in school?
No, like,
But cursing?
when you
Cursing.
come at night,
So
you say it.
I'm gonna go to the and say,
Like,
these are words that I can swear in.
Yeah, I can swear at
Oh,
school.
you get so riled up about
Swearing and cursing.
Right?
You're like, no.
But you better give them the whole context there.
Oh, I don't think so.
All right, next part. Let's say that we had a population of 100 people, and the growth rate is 5% per year. So growth rate is 5% per year on this population, or whatever we want to do, or whatever this element is. And the idea is that I want to know how many years, in terms of years, how many years did it take for me to grow to 350 people? This is my last problem.
that. It's 5%.
5% per year, 350 people. Do we need to use E? We wouldn't need to.
No, you don't need
The reason being is that they gave me a percent. I can use the one with the A0, the initial pop, what my total pop I want to get to, my rate, and what the time is. So I can use that A number, A0, R to the T. Now why I can do this is because I'm not looking for a growth rate exponentially. They already gave me 5%. So I'm growing, so that means I can just type it like this. I'm growing 5% on top of the population every year. My initial population is 100 people, and I want to hit 350, if that makes sense to you. I want to know how many years it will take me to get there. You see when you want to use E and when you don't. I want to use E if I have to calculate what my growth rate is. They didn't give me the percent right away. If they give me the percent when I'm growing by, I can just go immediately to this formula because that's easier. Because they're the same formula. They are one and the same. I can convert from one to the other. So now, to do this, I would divide the 100 over first, because I want to get the thing with the power by itself. So this turns out to be 3.5. Now what do I need to do?
Natural like
Not natural log, but regular log. The reason why, there's no e's on this problem. So I can just take the log of both sides. Log of 3.5, log of 1.05 to the t, and what will happen here, that t will drop out front, the t will drop out, like that, so it's being multiplied on the front, because that works on every type of logarithm. And then the last step is to divide that thing over. To get t by itself, divide this number over to the other side. So log of 3.5 divided by log of 1.05. And this will give me my t in terms of years. Because this, how I know it's in per year, the percent was per year. So that's what this percent's going by. If it was per minute, this is how many minutes it would take. And that's the beauty of these formulas. You can go by any time frame depending on what your rate is. So what do we get when we divide those out? So I want to make sure we know how to type those in. How many years will it take for me to go from 100?
Estimating 5.
25.6. So about 25 and a half years. The 0.6, if I take that times 365, it's 246 day of the year. So we're nearly at the end. So you can kind of figure out what day, what hour, what minute that would be. So you can calculate it down. Now, why does this take so long? We're only going up by 5%. So 5% growth on 100 people after the first year is what? 105 people? Then we're going 5% off of that population, 5% off that next one. So it does grow. It won't take long, but 25 years we grew, we more than doubled. We doubled